Thank you for watching this video about mobile robot obstacle avoidance based on optical flow images in motion planning. This was presented in South Annual Conference 2025, Chiang Mai, Thailand. As you can see in this video, the robot has to avoid obstacles for autonomous navigation. So, motion planning for obstacle avoidance is one of the essential capabilities required for mobile robots. Okay, let us first define what the motion planning is. Motion planning is to determine linear and angular velocities as outputs based on sensor inputs such as camera images. Dynamic obstacles such as pedestrians are the primary targets for avoidance. For dynamic obstacles, we have proposed a CNN-based motion planner for collision avoidance. LSTM was integrated with the CNN to consider the time series relationship between image input and their corresponding motion outputs. The motion planner was developed using imitation learning through motion instructions. As a result, the robot utilizing the motion planner successfully avoided dynamic obstacles at a greater distance than static obstacles, as can be seen in these videos. However, dynamic obstacle can move at various velocities. Consequently, if a robot plans its avoidance motion based only on relative position, it may fail to avoid obstacles and collide with them. This collision can be prevented if the robot avoided the obstacle to the left. In other words, the collision occurred because the robot planned its avoidance motion while ignoring the directional component of the obstacle's velocity. So our goal in this work is to enable the robot to plan avoidance motions based not only on the obstacle's position, but also in its velocity. For dynamic obstacles, the directional component of the velocity is important information. Therefore, we focus on the optical flow of the obstacle in RGB images and propose a motion planner based on CNN for optical flow image inputs. This is because optical flow represents the moving direction of an obstacle on an image plane. So the optical flow for all image pixels is first estimated. For a given pixel, the horizontal and vertical components of the optical flow are denoted as UX and UY. The direction of optical flow theta x is then calculated, as you can see here. Moreover, the magnitude dx is calculated, as you can see here. Based on this direction and magnitude, the optical flow is visualized by converting it into the HSV color space, as can be seen in these videos. In the optical flow image, an obstacle moving from left to right is colored red, while the one moving from right to left is colored blue. In other words, different moving directions are represented by different colors. Therefore, the road can consider the moving direction based on the colors and avoid dynamic obstacles. By the way, given a fixed camera, the optical flow is estimated only from dynamic obstacles in the image. However, when the robot moves, optical flow is estimated not only from the obstacles but also from the background. So the optical flow of obstacle is cropped from the optical flow image through object detection. As you can see in this figure, the optical flow of only the obstacle is visualized. Hereafter, the optical flow image and optical flow cropped image are abbreviated as IOF and IOFC respectively. In this work, there three cameras are used to expand the robot's field of view. In this case, the center and right images contain no obstacles. If these entirely black images are used as inputs to the CNN, it becomes difficult to optimize the convolutional filters for extracting image features. For this problem, these optical flow cropped images are horizontally concatenated. This panoramic optical flow cropped image is abbreviated as IOFCP. This image ensures convolutional filters to be correctly optimized through imitation learning. Here, let me show you three types of motion planners based on CNN with LSTM. These motion planners have different image inputs. These two motion planners use panoramic optical flow images or panoramic optical flow cropped images as inputs. The panoramic optical flow image is generated by simply concatenating three optical flow images horizontally. In the pseudo motion planner, each optical flow cropped image from the three viewpoint is used as an input. In the fully connected layer, linear and angular velocities from the previous time step are used as additional inputs, while the goal direction is fed into the fifth layer. Finally, in the output layer, the next linear and angular velocities are derived. All the motion planners are developed using imitation learning based on motion instructions. In the environment as shown in this occupancy grid map, an expert instructs a robot to move toward the goal destination, which is 15 meters ahead of the start positions. Meanwhile, a person walks in the indicated direction from either A or B as a dynamic obstacle at the speed of 1.0 meter per second. Since the walking speed is faster than the robot, a collision may occur if the robot avoids obstacle A from right and obstacle B from the left. To prevent the collision, the robot is instructed to avoid obstacle A from the left, obstacle B from the right. As a result of imitation learning, over 400 epochs, the loss values for the motion planners were minimized at 168th, 77th, and 107th epoch, respectively. So these optimized policies are used as a motion planner for autonomous navigation. This table shows the number of trials in which the robot successfully reached the goal in the environments where the desired motions were instructed by the expert. So these environments are known to the robot. First, the robot using motion planner 168 successfully completed all autonomous navigation in all 10 trials. It is noticeable that the robot avoided obstacle A from the left and obstacle B from the right as instructed by the expert. In contrast, the robot using motion planner 77 reached the goal only twice in the environment with obstacle A. The robot using this motion planner 107 failed in all trials. In all failed cases, the robot collided with the obstacles. Regarding these differences in navigation performance between the motion planners, we compare the ratio of completely black images in the dataset D used for imitation learning. The ratio of the panoramic optical flow cropped images was 28%. On the other hand, the ratios of the optical flow cropped images were 79, 76, and 91% for the left, center, and right images, respectively. As a result, the convolutional filters of the motion planner 168 were more correctly optimized, and this enabled the robot to successfully avoid obstacles. To further analyze the advantage of this motion planner 168, we examine the feature maps extracted in the second convolutional layers of these two motion planners 168 and 107. In these figures, three RGB images were horizontally concatenated to create a panoramic view. In these RGB images, captured at two time steps, a walking person, B, can be seen near the middle light. This figure shows the panoramic optical flow cropped image generated from the top RGB images. For this image input, this figure shows that features were extracted only from the obstacle. In contrast, for the panoramic optical flow image, features were extracted not only from the obstacle, but also from the entire background. By comparing these feature maps, we found that using panoramic optical flow cropped images allow the robot to plan the motion, particularly focusing only on the moving direction of the obstacle. Based on the results of navigation trial in the known environments, the motion planner with the highest performance, which is 168, was applied to the robot for navigation trials in a known environment, as illustrated in these figures, to evaluate its generalization capability. In the first environment, obstacles C to E were placed at positions different from A and B. A person walks in the direction indicated by the arrows. In the second environment, the person is standing at position F, located 5 meters ahead of the start position, serving as a static obstacle. The optical flows of dynamic obstacle E and static obstacle F are relatively smaller compared to the other two dynamic obstacles, C and D. The robot was not instructed to avoid these obstacles, so these environments with the obstacles are unknown to the robot. As a result, the robot successfully achieved autonomous navigation, including obstacle avoidance in all trials, as can be seen from the navigation trajectories. First, the robot successfully avoided obstacles C and D by moving behind them, just as it was instructed for obstacle A and B. This result indicates that the robot planned its avoidance motions by particularly focusing on the moving directions of the obstacles. Moreover, the robot successfully avoided obstacles E and F, which had smaller optical flows compared to obstacles C and D, from the left for time and from the right ones, respectively. In conclusion, we propose a CNN-based motion planner with optical flow images to enable the robot to plan avoidance motions based on varieties of dynamic obstacles. Through navigation experiments, we demonstrated that the robot using the proposed motion planner moved autonomously not only in known environments, but also in unknown environments with enhanced generalization capability. Additionally, the robot successfully avoided both dynamic and static obstacles with smaller optical flows and reached the goal destination. This is due to the relative change in the appearance of the obstacles in the image as the robot moved. As you can see in these figures, the optical flows were highlighted in red. So robot recognized that the obstacle was moving from left to right and consequently avoided it by moving to the left. These results show the effectiveness of the proposed motion planner, which utilizes panoramic optical flow cropped images as inputs. Okay, that concludes my presentation. Thank you very much for your attention.